Alright, so we have already proved theorem 572. Let's just go through the statement once more. Here we have a polynomial p over some field f which is solvable by radicals over f. Then the Galois group of px over f is also a solvable group. We have already proved this. Now next come to remarks about all these things. The first remark is that the converse of this theorem is also true. In other words, if the Galois group of px over f is a solvable group, then px is also solvable by radicals over f. We are, however, not going to establish this fact. It's merely a remark that we have to take for granted. There is another remark. If you recall, we were under the assumption that f contains all the nth roots of unity for all positive integers n. But this theorem and its converse are both true even when f does not contain roots of unity. So that means even if we relax this condition, then also both the theorem as well as its converse are true. And that also is just kept like this without any proof. Instead, we complete the section by finally having this theorem, Abel's theorem, which is that the general polynomial of degree at least 5 is not solvable by radicals. So let us first write the statement and then we see the proof. The statement is just that what I said just now. The general polynomial of degree n, where n is at least 5, is not solvable by radicals. And let's now see the proof. In the proof, in the beginning itself, we are going to recall something from theorem 563. That means our main section where we developed Galois theory there. We know from theorem 563 that if this field is the field of rational functions. You recall this field. The field of rational functions in the variables ai. In these variables, what do the elements of this field look like? They are quotients of polynomial expressions in these variables. Okay. Then the Galois group of this polynomial a1 t to the power n minus 1, and the terms go like this, plus an minus 1 t plus an. The Galois group of this general degree n polynomial, where this n of course is this n, okay, which is at least 5, over this field of rational functions is Sn, the symmetric group of degree n. And we have already proved that for this type of n, where n is at least 5, Sn is not solvable. Okay, and that result is theorem 571 by theorem 571, Sn is not a solvable group. If you want to write, you can mention for all n greater than or equal to 5, but because we have n is of that type, so I am not repeating that again. So I simply write that Sn is non-solvable. But then of course, by the previous theorem, I mean the one that we proved in the previous video, our polynomial cannot be solvable by radicals over the field of rational numbers. And that theorem of course is 572. So, by theorem 572, this is not solvable by radicals over this field of rational functions. And solvability by radicals over this, in other words, is solvability by radicals in general, for the general polynomial where these are also variable. Okay. And that's why the general nth degree polynomial is not solvable by radicals if n is at least 5. So the proof ends here itself, and the section also ends here. So after this we have the exercises, which we will do as many as we can, and there is only one more section left in field theory, which I think is Galois group over rational, something like that. Okay, so we will see what that thing is, what that section contains, once we complete the exercises fully. And that's just it. This is a small video because we had only this much left for us. What do we have tomorrow? Tomorrow we have again, oh yes, class 11 miscellaneous exercises. Miscellaneous examples. First we will go through examples. That means tomorrow I have to film a video, and the exercises will come only after that. So see you with that tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.